We now look at Rsa encryption and decryption. Okay, Rsa is the initials of three mathematicians who invented this algorithm in 1978. Okay, so it involves the following parameters. So we let P and Q be prime numbers, and then let N be the product of P and Q, which is sometimes called a semi-prime. Okay, it is almost a prime, but not exactly prime. And then you choose, okay, choose E such that GCD E phi of n is equal to 1. Okay, now let, because GCD E comma phi of n is equal to 1, inverse, so we let D be the inverse of E mod phi of n. This means i.e. D times E, or let me use ED, is congruent to 1 mod phi of n. Okay, so now to encrypt, so let me let n be a plain text represented as an integer, which is less than n. So let n be less than n. Then to encrypt, we use the, so m to the e is power mod n. Okay, and to decrypt, we will do, so this we will do c to the d's power mod n, and we are going to show that it is equal to m. Okay, so this will show will be shown in the next slide. Will be shown. So that means, okay, so what is public? So public key is an E, 2 parameters. Private key, okay. Well, we can just say E is a public key. So public key is E, private key is D, and N is no is a public parameters is, well, actually N will be part of the key, so let me just put it here. Okay, and P and Q must be kept private. So let's say D, P, Q must be kept private. So that is RSA. So so that means for each person. So let's say we have. So let me start a new screen. So let me first prove that encryption works. So now we prove that C to B N returns the original plain text. Okay, so this is proof. There are 2 different ways to prove it. So one way uses the Chinese remainder theorem. The other one doesn't. So the one I'm going to present here does not use the Chinese remainder theorem. So this proof has 2 cases. Okay, so case 1 is a general case. We assume that GCD M and N is equal to 1. So which means that M is relatively prime to N. All right, then by Euler's theorem, we know that M to the phi of N is congruent to 1 mod N. Okay, in other words, M to the phi of N mod N is equal to 1. So now we know since ED is congruent to 1 mod phi of N, it means that there exists a K such that ED is equal to K times phi of n plus 1. Okay, so now c to the d's power my n is equal to, we know that c is m to the e's power my n, so we just plug it in, and then my n. So this d will go in, so that's ed my n. So now we're getting is m. So ed is k phi of n plus 1 my n. So this will be m phi of n, and then times k times n my n. So my n can go in. So that is m phi of n my n k m my n. Okay, so this from Euler's theorem, we know it is equal to 1, and then times n, m my n. So then it is equal to m, because m is less than n. So that is case 1. Case 2 is that GCD m and n is not equal to 1. So from here, then we know either m contains either, so that means m either contains p as a factor, or contains q as a factor, but not both. Because otherwise, if m contains both p and q, then m contains n as a factor, which violates contradicting to m less than n. So m will either contain p as a factor or q, or contain q as a factor, but not both. So without loss of generality, assume that GCD MP is equal to 1. So we assume that M does not contain P as a factor. So then by Fermat's little theorem, we have m to the p minus 1's n to the p minus 1's power is congruent to 1 mod p. Okay, so that means C. So now we get C to the d's power mod p is equal to okay, so let me do this. Let me do this. So we have, so I start from here. Let's say m k phi of n mod p. So this is equal to m k p minus 1 times q minus 1 mod p. And this is equal to m p minus 1 mod p k times q minus 1 mod p. So this is congruent to 1. So this is equal to 1 k q minus 1 mod p, and it is equal to 1. Okay, that means so that means hence there exists a integer, let's call it u. There exists an integer u such that m k phi of n is equal to u times p plus 1. Okay, and since m contains q as a factor, we have m, which is equal to v times q for some integer v. Okay, so now what we are getting is we want m to the k phi of n plus 1. So this then is equal to m k phi of n times m. So m to the k phi of n is equal to u p plus 1 m. So that is u p m plus m Now, because M is equal to V times Q, so that we get is U, V, P, Q plus M. So this is UV, so this is integer, so product of it is integer. So P times Q is N plus M. Okay. Hence, so let me put it here, hence, C to the D my N is equal to M to the K phi of N plus 1 my N. And so that's equal to this, my N, and this N, my N is 0, so what's get is M, my N, okay, so my N, which is M. So that is the proof. So now to apply Alice and Bob. Okay, so Bob will select a P, Q, N is equal to P times Q, and it selects E such that GCD and phi of N is 1, and D is congruent, is inverse of E mod phi of N. Okay, so now this is Bob's. So this Bob's RSA. So let me call it PB, QB, NB. So indicate this is Bob's key. Okay, so this is Bob's key. So then there's a public key. So Bob's public key will be EB, NB, and private key will be DB, NB. All right, so Alice will do the same. So she picks PA, QA, 2 prime numbers, computes NA, which is PA times QA, and selects EA such that GCD of EA and phi of NA is 1, and DA is just the inverse of E A mod NA, and then the public key is EA NA, private key is DA NA. So if Alice generates a secret key, KA for AES and wants to send a message M. Okay, so to Bob. So what Alice can do is to encrypt M using EA. So this is encrypted. And then it sends RA, but this time it uses Bob's public key. So this is RSA. So let me just use RSA. Okay. Uses is public key EB, NB, and KA. So it sends this to Bob. So now M is encrypted, so no one else can see can see M because no one else knows KA. So this KA now is encrypted using Bob's public key. Nobody else has Bob's private key, so they cannot decrypt this message to CKA, but Bob can. So Bob can decrypt. So this KA at Bob's size will be just using DB and B of CA. So let's call this CA. Okay. So now, how secure it is, right? So for this RSA, so for RSA, we need forward efficiency. So forward efficiency can be guaranteed by fast exponentiation. Exponentiation algorithm and Euclidean algorithm. So this is to compute encryption and decryption. And this Euclidean algorithm computes GCD phi of n is 1, so finds E, and also then use fast exponentiation to compute D. So compute inverse of E mod phi of n. This is really is equal to E to the phi of n minus 1 mod phi of n. Okay. The reason is because of this, by Euler's theorem, we have e to the phi of n is congruent to 1, not phi of n. So E inverse will just be minus 1. Okay, so you multiply E together here, then you get to the unit. Okay, so that's fast efficiency. So fast efficiency is guaranteed. But it's not linear. It's not linear time algorithm. Okay. It's not linear time. It's fast, but not linear time. As a matter of fact, it is quadratic time. Quadratic time. The reason is during the fast exponentiation, you need to involve a multiplication of two numbers, which is less than n, but could be close to n. So this will be for 2 times either the length of E times, okay, and for this, and also plus 2D for this, and then to multiply two numbers, of size n, of size log n, okay, would need about quadratic time. Using a more sophisticated multiplication of two numbers of size. So this is size. So you can reduce this to something like this, 1.585 or something, but this is still not linear. So this is super linear. So it is not super fast, but it's still doable, particularly when, particularly for short messages. So this is for short messages. So of course the secret key is either 128 bits long. So that's short. So this is fast efficiency. How about backward intratability? Okay, so so basically, it's a given n. finding P or Q. So this is an integer factorization. Is integer factorization, which is believed to be computationally difficult. Okay, so people have tried doing this for several hundred years now, and we still don't have efficient, by efficient means we still don't have polynomial time algorithms to do it. On a separate note, just as discrete log problem, if we have a on a theoretical quantum computing model, integer factorization can be done in polynomial time. Okay, so that is backward intractability. It relies on the difficulty of factoring an integer. And then I have the last one, the third, commutability. Okay, so obviously that encryption and decryption is the same. So encryption and decryption is the same algorithm, but just with different keys. Okay, so the keys can also exchange. So in other words, if you have, let's say, E, K, 1, M, and D, K, 2. So this is really is M, K1, M, and then K2, N. So then this is equal to M, K1, K2, N. So you could have exchange. You could have, let's say, you could have K1, E2M because of this, right? So we have commutability. Okay, so this is Rsa.